So welcome to this session. This session, we are going to prove whether a given set defined by addition and scalar multiplication defines a vector space. So the problem reads, let R plus denote the set of positive real numbers. So we define addition on this set by x plus y is given by xy. So this addition operation on this set. And then scalar multiplication, c times x is given by x raised power c, where x and y are elements in the set R plus, and c the any real number. So the question is to prove whether the set R plus is a vector space. So to prove that, we have to check the 10 axioms of a vector space. And with this specific example, because we have already defined addition and multiplication, then we'll have to prove the remaining 8 properties. So property 1, so 1, commutativity. So we check if we have elements u, v in this set R plus, then u plus v, this addition in this set, is an element in this set R plus. So by definition, we have u plus v is given by uv. I remember u and v are just positive real numbers. So product of two positive real numbers, this is like the usual multiplication. So this can as well be written as v times u. And if u plus v is given by uv, then v u is the same as v with this unusual addition sign u. So therefore, u plus v is equals to v plus u. So i.e. commutativity with respect to this addition holds on this set R plus. Number 2, let's prove associativity. Now for associativity, we check that if we have, so we check that if u, v, and w are elements in this set R plus, then u plus w plus, okay, u plus v plus w u plus v plus w is the same as u plus v plus w. Now let's start by u plus v and then plus w. By definition, u plus v is given by u v and then plus w. And then by definition, so this is just like one element. So it'll be simply UV and then W. And you see, this can as well be written as UVW, since U, V, and W are associative on R. And then by writing this way, this can be defined as U plus and then V W. And then this is the same thing as writing U plus. Now VW is the same as V plus W. So we started with U plus V and then plus W is giving us U plus V plus W. So therefore, associativity holds associativity with respect to this addition holds on R plus. So the property for associativity with respect to this addition holds. Number 3, additive identity. Now for additive identity, we check that they exist, say an element Y in R plus such that if I take U and then plus this Y, then I get U, where U is still an element in R plus. Now, since U plus Y by definition will be given by U Y, then for U plus Y to be U, then Y must be 1, so that 1 times U is U. Hence, additive identity on R plus exists and is 1. So 1 is the element whose addition with any element in R plus will give you the same element that you are adding to that element with this given definition of addition. Number 4, additive inverse. Now for additive inverse, we check that. So we check that there exists an element, say Y, in this set R plus, such that for any element U in this set R plus, then if I take that U, I add to Y, I should get the additive identity whose value are found to be 1. And so, since U plus Y will be given by UY, then for U plus Y to be 1, then y must be 1 over u. So that if I say u plus 1 over u, by definition it will be u multiplied by 1 over u, which is 1. And because R plus consists of all those real numbers which are positive, so there's no 0. So we can always have the reciprocal of every element being defined. So therefore, additive inverse exists on R plus and for any element u in R plus, its additive inverse is its reciprocal 1 over u. So note that the way we are defining the identity and inverse for this set is different from the usual one, saying that the inverse of u is minus u. So the definition of the inverse of the identity depends on the set we are dealing with. And then that was number 4, additive inverse. Number 5. So we are to go to closure with respect to scalar multiplication, but that one has already been defined. So let's go to what we call distributivity. So we check that if I have a real number alpha and I have 2 elements u and v in this set R plus, then if I say alpha times u plus v, then I need to get alpha times u plus alpha times v. So this is what you need to check. Now, alpha times u plus v is the same as alpha times. Now, remember u and v are taken from R plus, and any addition of elements in R plus, u plus v will be given by uv. So this is u v. And then next step, if you have a scalar multiplying any element in R plus, then the answer is given by taking that element in R plus and raising it to power alpha. This by definition. And this also by definition. Definition of addition in R plus, and this definition of multiplication in R plus. So loss of indices u, v, remember u and v are just positive real numbers. So when you raise to power alpha, it's the same as u raised to power alpha, v raised to power alpha. Law of indices. Now, we can as well redefine this one. So we have product of 2 positive real numbers in R plus. So if we have a product of these 2, then from the definition of this result, this must have come from u raised to power alpha and then plus v raised to power alpha. Since we know that if you have x plus y, then you have xy. So xy means x plus y in this given set. So that's why from this step, you have this, and then that reduces to alpha times u plus alpha times v, since if you have any c multiplied by x, then the answer is always given by x raised power c. So when you have x raised power c, then it must have come from c times x, according to the definition on this set. So this is alpha times u plus v gives us this. And actually, this is what we are supposed to prove. So therefore, distributivity, you can just say, therefore, this multiplication is distributive with respect to this addition, i.e., distributivity property holds. And then we also have another type of distributivity where we have now two scalars. So that's next one is number 6. Still distributivity, but now involving two scalars and one vector from the set R plus, distributivity. So this second kind of distributivity, we check that. So this one we check that given two scalars alpha and beta are picked from the set of real numbers, then if you have any element you picked from the set R plus, then distributivity still holds. So we check that given any two scalars alpha and beta, and you pick an element in R plus, then if I sum these two scalars, alpha plus beta, I multiply by u, then I get alpha multiplied by u, and then plus beta multiplied by u. Now, so remember here, this I'm writing with visual addition because this is the property we need to prove. So this is not the addition specified in the set. This is the property that you have to check at the sum of two scalars multiplied by the vector from the set of interest give this result. So alpha plus beta times u by definition will be given by, so we define this multiplication. Remember, if I have C, a scalar multiplied by an element x in R plus, I get that element raised power the scalar. So the same thing, alpha plus beta is still just a scalar because sum of two scalars is a scalar. So this is u raised power alpha plus beta. This is the definition of this type of multiplication specifically for this set. And then by law of indices, u raised power alpha plus beta, the same as u raised power alpha times u raised power beta. This is law of indices. And then you remember that if I have x plus y. On this specific set, this addition is specified as xy. Now you see u raised power alpha is a positive real number. U raised power beta is also a positive real number. So this, like I have xy, my x is u raised power alpha, my y is u raised power beta. So this must have come from u raised power alpha plus, now this unusual addition, u raised power beta from this definition. Now, so just say since this is what we have. And then by definition, if you have a scalar, you multiply by any element x, you get that x raised power the scalar. So therefore that definition of multiplication on this set will help us to define this. So this is the same as alpha multiplied by u plus beta multiplied by u. And actually that's the property that you wanted to prove. So distributivity holds. And then a second last property, associativity with respect to scalar multiplication. For this one, we check that if I have C, I multiply by, I have alpha, I multiply by beta, and then multiplied by an element u, then it's the same thing as saying C alpha times beta, and then multiplied by u. Now, this is how we start. Alpha multiplied by beta times u. I remember alpha, beta are any real numbers, but u is specifically a positive real number from this set, R plus. So this will be given by alpha times beta u, by definition is u raised power beta. Since if I have an element C times x, then this is the same as x raised power C. That's the definition of scalar multiplication on this set. Next, this is the same as u raised power beta raised power alpha, since C multiplied by x is the same as x raised power C. This is the definition of scalar multiplication on this set. And then this can be written as u raised power alpha beta. This is law of indices. And then, since we know that if I have x raised power C, then I must have C times x. Then I can write this one as u alpha times beta, and then multiplied by alpha times beta multiplied by this u. Or this is the definition of scalar multiplication on this set, R plus. So we have successfully shown that alpha times beta times u is giving us alpha beta times u. And so therefore, associativity with respect to scalar multiplication holds on R. falls on R plus, not R. R plus. And then finally, number 8, this was 7. Number 8 is to show that on R plus, we have what we call multiplicative identity. So number 8, multiplicative identity. Now here we show that, or check that if I take 1, I multiply by u, then I get u, where 1 is a real number, and then u is an element taken from this set, R plus. Now, 1 times u, by definition, because 1 is a scalar, is 1 raised power u. And you see 1 raised power u, lots of things is just the same as u. So this shows that 1 times u equals to u, and therefore multiplicative identity on R plus exists, and say holds. Now, since all the axioms of a vector space have been satisfied, therefore we conclude that the set given, R plus, is a vector space. Hence, R plus, together with this addition and multiplication, is a vector space. So that's how I prove that.